All right, okay. Hello, good evening everyone, or good afternoon. So my name is Sugu. I'm the track host for this room today. I'm excited to introduce Fabrice Jammes, and who is a scientist. And he's going to talk about how science and containers and Kubernetes come together, how to containerize science projects. And without further ado, here's Fabrice.
Thank you so much. Hello. So nice to meet you. So yes, I'm Fabrice, and I work as a sysadmin and software developer also on the Large Synoptic Survey Telescope. So I will explain you what is this telescope, what the goal you want to achieve, and I will explain you also how we use CloudNative to put all the software stack, to manage all the software stack. So first, I will describe the telescope, okay? Then I will talk about Qserv, which is a database we have to manage all the star and galaxy catalogs in order to enable scientists to discover new stuff about the universe. And then I will talk about the benefit of CloudNative in our special use case, what it brings to us compared to regular infrastructure management. And then, And then I will compare on-premise infrastructure versus public cloud, because we use both, and now I have some experience on what they bring and what they prevent. So look, the telescope, it's the first research project in the US with a budget. It's $1 billion budget. And then it's a very large telescope. You can see the CCD. So compare it to the CCD of your phone, you see that it's much bigger. And for your information, 1 pixel, it will get 1 football soccer on the moon, you see. So each pixel, you see, we cover a large area of the sky. And then, yeah, this is the largest imager ever built for astronomy. So it will do kind of a movie of the sky. So we will have 6 filters. We will see 20,000 square degrees, which is a large area of the sky. And then we will visit the sky in each 3 days. And we will get around 60 petabytes of raw data. So 60 petabytes of raw images each year. So you see the telescope, it gets the raw data with this CCD, which is advanced silicon component, which is difficult to build. And then the data, we send it to data center. So we have a data center in France, in Lyon, and a data center in Urbana-Champaign University in Chicago. And so the data goes from Chile to the data center. The telescope is in Chile. So we build a special gigabit network connection also with Chile. And then we process the image in the data center, okay? And we build the star and galaxy catalog, which is the main component for science. Catalog, for example, the first one was built by Ptolemy a long time ago in Egypt. And then a French also at the 18th century, Messier, he built a famous catalog of 110 galaxies and stars. Okay, so catalog is a list of galaxies and stars with their physical properties. That's what we extract from the image during the data processing of the image. So we will get a 40 billion galaxy and star catalog, which is the largest the largest size we have for all telescopes this year. But the next telescope will be even bigger, of course. Each telescope, you get a new scale. So it's like, you know, when you do in chemistry, you need a lot of people to know if the chemistry is working, if the medicine is working. Then you need a lot of stars and galaxies to know the structure of your universe, to enable statistics on large scale. So there is the data, so the image, okay? It will be 38 petabytes of persisted image we will back up, okay? and we will generate half an exabyte of image. Because we need to do co-addition, okay? So in order to discover stars or galaxies which are not on any image, we co-addition the image. So we co-addition them if they are on the same region of the sky. So this reduces the noise, okay? And you can also discover new objects that are on no image. Okay, it's like if you take a photo with a longer exposure. So from this, we will build the catalog, okay? So we will have 47 billion objects. An object is a galaxy, for example, and we will have 9 trillion detection. For example, if a galaxy, you say Andromeda galaxy, it will be one line in the object table, and if you have 1,000 photos of the galaxy, you get it on 1,000 image, you will have 9 trillion detection. Excuse me, 1,000 line is the detection table, okay? So it's large data, but the relational model, this relational database, is quite simple because all the telescopes have basically this relational model. It doesn't change from one telescope to another, and telescope exists since a long time. Okay? We need also to keep the provenance of the data. So the provenance, which algorithm was used to discover the star, the image of the galaxy, and also which computer were used, which compiler was used. So we need to track the generation of the data from the photon, which go to the CCD, which is the CCD, to the bit which is stored in the computer. So we have all this metadata to keep. So now I will focus on the main product of one of the main product of the data access component for LSST, which is the petascale database for storing catalog. So this database is built at Stanford University, SLAC, the Linear Accelerator Center, so by 10 engineers, and also by myself, which is in France, because France collaborate at 5% of the budget to this project. And then also we have sysadmins in the large data center, so NCSA, it's 12,000 node data center. IN2P3 is a 1,000 node data center in France. And so here we have our development platform, because to develop and test at small scale, we need at least 50 nodes. Because you see, we will have maybe 500 or 1,000 nodes on production. So we need a cluster to test. Okay, so yes, we are on CloudNative, Kubernetes. We are working on preparing production, on enabling production. So also we do monitoring. We are preparing the production because the telescope will all run in 2022. Okay. So in the team for data access, it has a lot of tasks. Okay, so managing the image, managing the metadata, getting the alert also, because in astronomy, when you find something like a supernova or a transient object in the sky, we don't have a high definition. So we will, when we detect an object, we send an alert, and other telescope, they will, like telescopes which are in space, they will focus on this object to get its property. So it's a collaboration between all the telescopes. So yeah, we work about all of this, okay? The main project is this Qserv. This is a distributed database. For those who know Vitesse, it's a bit the same concept. So look, we split the sky in 20,000 parts. We call it chunk or shard. And then we distribute the shard on hollow node. It's a MariaDB database also. So if you have 20,000 shards and 1,000 nodes, you will have 20 shards on each node. If you have 5 petabytes of data, you will have 5 terabytes on each node. So 5 terabytes and 20 database, one MySQL node, it can handle that. It can manage the index and stuff like that. So we distribute this, and then the user, he has a MySQL client, he launches a query with his MySQL client, he goes to C++ code, okay, which is a custom-made C++ code. And then we have a parser. We analyze the query. For example, if the query is a select count star from object, you want to count all the objects, a very simple query. Then we understand the semantic of the query. We rewrite 20,000 chunk query for all the chunk. So which counts the object in each chunk. We distribute it with a middleware which is called Xroot. The developer is embedded in the team. Xroot, it's managed also petabyte of data at CERN in production. So this is a well-working, robust middleware. And then we distribute this. We have 20,000 threads. We wait for the 20,000 count. The result goes back to what we call a temporary result table on the master. We have the 20 in this table. We have the 20,000 count. We perform an aggregation query, which sum all the count, and we return the result to the user. Okay. So this is for a simple example, but it works also for join and more complex query. We do not support all the SQL, but we try to support all the SQL that are required by astronomers. So here is our test, one of our test or development platforms. You see, it's in Lyon. So this is the 2 rack. It's 50 nodes. It was offered by Dell five years ago. Dell is our sponsor. And then, yeah, now it's a bit old hardware, but we perform tests and we have loaded 250 terabytes of data inside this platform, and we run performance tests. It's a synthesized data because real data set with real star and real galaxy, it doesn't exist at this scale. So we need to generate synthesized data. We also have the same an equivalent infrastructure, which is in Chicago, in Urbana-Champaign. And here we load real data from the WISE telescope, which is a recent telescope. And here we have 25 terabyte data set with real data. And astronomers and cosmologists, they are launching query against this data, and so they can do science. The first cluster, it's only for performance. No scientists use that because you can't do science. Okay. So this is our test platform. This man is the manager of the world project, William Lane. He comes from ESA. And now I will explain you what are the benefits of cloud native in our context. Okay? So it was very difficult to install the code. The project started 10 years ago, and then at first we do not have container, we do not have Kubernetes. We have to reinstall all the code on. Sometimes we have 300 nodes. You know, we perform tests on 300 nodes. So we have to reinstall the code by hand with our custom procedure. And honestly, it was 1 month work each time. It was very long to rebuild the code. Developer, it was difficult for them to upgrade the code because there was not a real procedure. Everybody was trying to hack. Okay, so it was difficult to go to run our large scale, and we only run once a year. Okay, but then we go to cloud native and container because it brings lots of flexibility in deploying the software, and we are in development, so we need to deploy the software a lot, maybe several times a day. So what we do, the developer now, on this vacation, he push the code to the GitHub repository. The code is open source. You can get it on GitHub on the LSST Qserv repository. And then he push the code. So it triggers a Travis CI build. Travis, it builds the containers. It installs Minikube. It runs a Qserv cluster with a small amount of data. It checks that the queries are working, and if the queries are working, it pushes the container to the Docker hub. Okay? So you are a developer, you push, you get a coffee, you come back. If you say Travis is green, you can use the container which is built by Travis. There is the version is the hash of the commit. It's easy to use. Then the developer, what he can do, he can use previously OpenStack. We have OpenStack, but the engineer has left for private company, so we don't have no more OpenStack maintained in my lab. But now we use JCloud. We are working closely with Google. And then you can spawn a cluster, okay, OpenStack cluster in the cloud. And then you go to use kube control, launch a Qserv status script, and it will spawn the container on the cluster. Okay? So you see, you have two actions. First, you push your code. Second, you start the cluster and you launch a container, or you can use an existing cluster. Okay? So here we have done this test. So we are running it on OpenStack for two years. Now we are using Google because it's more user-friendly, no maintenance. And it's cheap because you have 80% discount on the node because you use Google preemptive machine. So it's €2 a day for a 3-node cluster at Google. So it's okay when you use it. If you don't use it, you don't pay. And then at Google also we have loaded a 35 terabyte dataset. So the white dataset I was talking to you before to compare performance between our bare metal platform and the GKI. Okay, and we were running also experiment on local safe with OpenStack, but the engineer has left. So OpenStack, we have no maintainer now. So we and Google appear at the same time, so we switched to Google. So now, if you are in our data center, so on our bare metal platform, so in Lyon and Chicago, then the user, the developer, he can SSH to the platform, and he runs the same install script than on the cloud platform, okay? And then this will install Qserv also on the bare metal with the very same install script, okay? So it's easy to install anywhere the code with the same procedure. That's what brings Kubernetes to us, one of the main feature. Because you see, this software was complex it was complex to get this software Qserv up and running on large cluster with lots of versions because it's always moving. If you go to the CI also, so when the developer pushes the code, what does it do to have this? So it builds a container, so it checks the build is working, it tags the container with the hash of the commit, then it starts Minikube, okay, inside Travis. It's pretty easy to do that. There's lots of documentation on the internet. Then it starts the Qserv pod, Qserv cluster inside Minikube. We launch integration test at small scale, and then it pushes the container to the hub. Okay, and this is the very same install script than on the bare metal cluster and on the cloud development platform. Okay, so we check also the install script work. So that's what CloudNative brings to us. Okay, so this is the detail of our pod and stateful set and replica set we have in our database. We have multiple components. I won't go into the detail. But what it brings to us here, we have automatic scaling. So we were at Google on 40 nodes, and we wanted to test on 50 nodes to have the very same clusters and on our data center. And in a few seconds, we have 10 more nodes, and we have the Qserv running on it. So it was pretty impressive compared to the work you need to do when you want to scale inside your own data center. So it was thanks to Google and also to Kubernetes. We have also container scheduling. We are IO driven. So IOPS are our limit. So we need to schedule a pod aside each volume, each chunk of the sky. And then Kubernetes, it can do this very well. Okay, you just have to put it in the configuration of your pod, and your pod get aside your data. It's easy. And then we use also auto-healing, because when you have 50 nodes, there is always one node which is broken or which is not feeling well. And when you scale, the more you scale, the more you have problem. And this is useful to restart your container. Okay, this is pretty useful. But as said my colleague, you don't want also it to restart because it could hide bugs. So in production, if it restarts one time on 6 months, it's not a big deal. But if you save your night, you don't have to do maintenance during the night, it's okay. But yeah, you don't want it to restart. You want the software to work, of course. But yeah, it can be an interesting feature if you don't use it a lot. Then we have also continuous deployment, as I showed to you. It's a manual, but we are going towards something which is more automated. We have volume management, which is interesting because, yeah, we have stateful set with persistent volume claim template. I won't go inside the detail, but Kubernetes manages the storage. And when you move from, we have local disk on our cluster, and we go to Google to use Google persistent disk with the SAN. And when we move, we do not have to change the script. We run the startup script, it attaches your local disk on our cluster, and we go to Google, and it creates Google persistent disk and attach gem to the pod without changing the script. So this is very powerful. You don't have to manage the storage. So you can delegate this to the infrastructure. Also, the monitoring is pretty easy. We'll try to deploy our own. Now we are dependent on the monitoring of the data center. Each data center has its own constraint, and so we have to fit between this constraint, and it's difficult. But maybe with Prometheus, we will provide a standard stack of monitoring, and this is great because if you install to a new customer, a new user, you can also deploy the monitoring in seconds. So this is interesting, or at least deploy an API for monitoring. Health check also is interesting because we have lots of services, you see lots of processes which are running, and there is always a process which is not working very well. It's normal at large scale. And so you can embed the probe inside the pod. Before you were using, for example, Nagios, and you have to check the Nagios, install Nagios, maintain Nagios. And then now you can embed the probe inside the pod, and then you know what is working or not working only by asking your DNS. You see, because when the probe is okay, it will register your pod inside the DNS. So all you have to do is you run a ping on the name of the pod, for example, and then you know it's ready. So you know to check if everything is working, you have the kube control. So it's like if you run a top on your laptop, you see all the pods which are running across your cluster, but in one place. And also, you can use the DNS, and you know it's running. So it's very convenient. And security also is a great feature, because now when we are on development platform, we want the developer to be root inside the container. So he can connect inside the container, open a shell, and install GDB, netstat, all these tools for debugging, you see. But we don't want it in production because it will be too dangerous. So with Kubernetes, you have something they call admission control. And if you do nothing, your pod run with no security. But with the same install script, you run against a well-configured Kubernetes cluster, and you will inject security. And the pod, you will inject YAML inside the pod for technical details, and the pod will run with low privilege. And so the developer does the same stuff, deployed on the development platform is root. On the production platform, the pod is very secure. And the Kubernetes can do that. But of course, the Kubernetes administrator has to manage that, but only one time. What's what they call pod security policy. Same thing for the network. You can define your firewall. The developer can define firewall and rules without having access to the machine. With Kubernetes is what they call network policy. So you can bring all of that everywhere. So, but the killer feature we have found is that portability. So we were able to move the application everywhere with no work. And before, we have moved the application everywhere, but with a lot of work. That was my job, indeed, in fact. And so each time there was to install the application on a new cluster, a new data center, I have 2 months. I say to my management, I will do only focus on the installation. And it was a red alarm, and we were installing and debugging. And now, last time we installed, it was on GKE, because Google, they offered us a promotion for $100,000 to test. We are collaborating with Google. And at GKE, it was installed in half a day, because we have to do some setup in the install script for the storage, because the storage is not the very same, so we have to generalize the management of the storage. And then the cluster was started, it was 1,000 core, 120 terabytes of data also, and we have 4 terabytes of memory, so pretty large cluster. It was started in maybe 1 hour, and 2 hours after a few changes in the YAML file for the Kubernetes, it was running. So you see, and now I think it may be more easier now because we have handled the generalized management of the storage, so we can even move easier to another cloud provider. So this is a good way. It's like me, each year I change my phone to go to a cheaper phone provider, you know, cheaper. And then this is the same thing. If your application is packaged inside it, you can move easily to the cheapest cloud provider. So now to finish, I will make a comparison between on-premise, what are the advantages of on-premise versus public cloud. What are the advantages of public cloud? Because I've tested both and now I have some idea of that. So what we are doing, we are different model. So the first model was running all the stack at home in blue, the software, the Kubernetes, and the infrastructure. And then with Google, we test running Qserv on top of Google Kubernetes engine. We have some experts from Google who helped us, but it was not so difficult. And also some Google experts, they take our data and they put it inside BigQuery and they compare the performance between all the three architectures. So I do not have the result for the BigQuery, but if you check on the internet Ross Thompson and LSST, and you will check there is a blog with all the explanation. So I will explain what is GKE briefly, how I see GKE as a user, but I think it's the same thing with Amazon or Azure. What I say, it's true for any cloud provider. So you see the GAFA, they deploy container at large scale, and so they put in their knowledge inside Kubernetes. And now, any of us, we can use Kubernetes and the benefit of that knowledge. But, yeah, we have to install Kubernetes at home. Okay? And this is a bit difficult because look, that's all the thing to do if you want to manage Kubernetes at home. So we do that also because we have both configuration. I think it's a very interesting job to manage a Kubernetes. But yeah, if it does not work, it's good to have also some support from experts. When you are alone at home, it might be difficult. So, okay, so that's what you have to do. It's complex. And furthermore, you have to maintain it in the long term, upgrade it and manage it. And it's complex also. So what Google they provide, it's a one-click Kubernetes. You click, and your Kubernetes is working. And you don't have to bother about it. So now I will describe what are the advantages and the cons of this setup. So you see, the advantage is that if you want to add new node, it's very easy. The support from Google is good because they know very well Kubernetes. And so they help us a lot in improving our setup. It's easy to set up development cluster. And if your data is not private, you can spawn a cluster and you don't have to manage about security. Because you spawn a cluster to any developer or any tester, and in second, it will work. And Google also, they have some nice proprietary features, which are very interesting and that you don't see, it will be difficult to implement it in your own cluster, like dynamic node provisioning. So if the cluster is too low, you can create new node on the fly. So also dynamic storage provisioning, so they can create disk. You start your application requires storage, and the storage comes magically. So it's interesting. The cons, that we found it very expensive. It was 100K for a 1 month test for 1% with 1% of the data. So it's very expensive, and I think we can't afford using Google. It's easy also to get stuck with proprietary feature because you see, for example, Google engineer, they don't see the very difference between what provides GKE and the pure Kubernetes. And so they can tell you, use this feature, it's very interesting, but it's only a Google feature. So when you go back at home, you don't have the feature. So you have to change your script to go back at home. So that's why it's good to run Kubernetes at home and know how it works. So when you go to the vendor, you can use only the standard feature and not the other one, or, to avoid lock-in. And so also it hides Kubernetes internal, so you don't know at all how it's working. And so sometimes if you want to performance, for example, or fine-tuning, you don't know how to do. Okay, it's a black box. And also we found that it was running slower than bare metal on 25%, but it's normal, I think, because they have SAN, remote storage, and us, we have local disk. But you see, Google is very flexible. You can start a lot of nodes very easily and fine-tune it on the infrastructure side. But if you want like local disk, it is not possible. So it's flexible in one way, but not in another way. So if you have your cluster at home, you will have flexibility because it's a do-it-yourself cluster. So you will build it on your own. So you can fine-tune. Here, for example, we can use local disk. Okay? But it will require skilled engineer. It's an interesting job because like the KubeADM installer is pretty nice, the tool is nice also. So you learn things and it's interesting. But for example, we had a security issue in January, so we have to upgrade Kubernetes. We are on CentOS, and the minor upgrade wasn't working because CentOS provides a package, but it wasn't working. So we have to upgrade to major upgrade to 1.13. We switched to Core DNS. Then Core DNS, the cache was not working well. So we fight during 10 days to fix the cache error. So you see, it's 2 weeks, a bit stressing. At Google, no problem. It always works. Okay? So yeah, both have pros and cons. And then also, because we have local disk, you can fine-tune the infrastructure, and it runs faster than private cloud. But this is because we need local disk. Okay? Or we don't know, but our stuff was designed to run on local disk. The cons is that it's difficult to retrieve the global cost because we have to maintain the building, you have the air conditioning, you have the maintenance, you have to pay sysadmin, you have to change the hardware, you have to pay maintenance for the hardware. So it's difficult to retrieve the global cost. So at Google, it's very easy. So it's interesting to know how it costs also. And it requires manpower also for setup, maintenance, and also hardware upgrade are difficult. When you want to change, now the hardware is a bit deprecated after 5 years, and we need to change 50 nodes. And honestly, you see, we need some 3,000K budget and find it and get the computer, change the computer. So it's at Google you click and you have your cluster in seconds. So you see it's different. And also it's difficult to rebuild the cluster from scratch. In Cloud Native, sometimes it's very useful to rebuild everything from scratch. So if you have a problem, you don't find the solution. You restart from scratch and you know you have described your infrastructure and you have what is running is what you have described. Here, it's true at the Kubernetes level, but below Kubernetes, the infrastructure is difficult to reinstall from scratch in production. And it's slow also because reinstalling a system on the production is more slow than starting a virtual machine. So that's why I see in pros and cons of both infrastructure. As a conclusion, I will say it's good to know the standard and respect the standard, and then you can choose which infrastructure you use and try different infrastructure, try to avoid the vendor lock-in. So if you have questions, I'll be pleased to answer, or we can discuss later also. Thank you.
Just a question about the data. Is it going to be publicly available? Are there any plans? Do you want to make it, open access?
Yes, the data, it's open access. So we don't have the data yet, but it will be open access. So one goal of the database is that users which have not contributed to paying the infrastructure, they will run slower query. So we have people from country who have paid the infrastructure, the query will run fast, and other people, it will run slower. But anybody in the world can get the 5 petascale dataset and handle it for free, of course. But the cost is inside the infrastructure. Yeah, most of the dataset for astronomers, they are always free, and there is they call it Virtual Observatory Alliance. So there is standards since a long time, so you can cross-match data from all the observatory, because it's a requirement in cosmology. So you can check for an object, and you want to get all the observation of the object for all the telescope. So they have this standard, and we are compliant to that. But the problem is that, you need 1,000 machines to handle the data. That's what it's complex, and anybody can't provide access to the data easy. We hope that Google may, when we will open the telescope, people, they eat a lot the database when we will, at the first data release during a few days. And we would like cloud provider to sponsor us, maybe, and provide free access to everybody to get the data during 2 or 3 days. Maybe not with a relational database, but something more simpler, but people, they can get access. And then, when the peak is finished, then we will go with regular tool. Could be, it requires infrastructure.
Okay. All right. Thank you very much.